Alright, time for another DraftPhysics.com, DebatePhysics.com also. Video presentation. Alright, Nick Lucid response video, and see if we can get him to engage in a discussion about the validity of the narrative provided by physics. Now, in this video, he's actually going to point out how the myth of the Stern-Gerlach experiment isn't the reality. And like most other physics experiments, it's an exaggeration and all of this hyperbole and whatnot about what is proven and what was established and blah, 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 blah. So you go back to the Eddington experiment, you go back to all of the nonsense. I mean, you can go all the way back to Leibniz and the claim that 4 pounds dropped 1 foot is the same energy as 1 pound dropped 4 feet. And 1 pound dropped 4 feet is only twice the velocity. So somehow 1 pound going twice as fast is somehow the same momentum, energy, capacity to do work as 4 pounds dropped 1 foot going 1 velocity. And it's nonsense. They won't argue it. They won't discuss it. It's absolute nonsense. There's no physics experiments that prove this nonsense. And yet that's the myth. And we all are expected to believe or be called names. All right, so anyway, Stern-Gerlach is the subject. And basically his claim is the silver atoms aren't magnets. Okay, they're getting thrown through this experiment. And clearly the 1950s version, that's all they're talking about is the fact that the silver atoms are magnetic. So, you know, right here we have a conflict in what the physicists say. And their argument, I will explain in more detail, and I will play his video, but just the brief of it is, I'm arguing that clearly atoms aren't what they claim them to be. The electrons don't have angular momentum. They're not spinning all over the place. It's just wrong. Okay, so not an accurate theory. It doesn't make any sense in so many ways. And clearly the electron itself spinning, it's like the moon spinning. It wouldn't mean anything. Now, the only way you can make it mean something is if it was polarized in the opposite direction of its spin, okay, in the sense that it had some sort of magnetic field and it was spinning north-south like this. Well, then you could say it could have some significance because it could do something. But a spinning moon isn't going to change anything. It's not going to make anything any different. It can't exercise any momentum on the system. Either the Earth or the sun or the whole solar system isn't going to care that the moon is spinning. It's just not going to matter. And their theory is that somehow this electron spinning is somehow moving the entire atom and swishing it all about. And there's no logic to it. So, yeah, I guess okay, I'll do first a quick diagram of the experiment and perhaps even just show this little bit here. This is the 50s or 60s version of the experiment, more kind of illustrating that no magnetic field, all the little atoms go straight. You increase the magnetic field, they start to spread out. That is, half of them go this way, half of them go that way. Then it comes, you know, more and more. The stronger the field, the more spread out they become. And so much so spread out is that some of them are disappearing. And so in the volume you have here, there's less volume here, and there's less volume here. If you add up these two wings, it wouldn't add up to this volume because some of them are now off the scale. They've moved so much. So the idea is, so let's do the drawing of the idea. All right. So I guess the first thing to point out is, I should have showed it in his video, but it doesn't really matter, I'll do it real quick. So there's a net positive nucleus. My argument is it's not all positive. It's net positive. It has neutrons in it. Neutrons are protons and electrons. So it has twice as many protons as electrons if you consider a neutron a composite object, which I think is perfectly reasonable and it actually was Rutherford's understanding of a nucleus before the invention of protons. He considered the nucleus to have electrons in it. But anyway, and so the new electrons, my argument would be in standard locations based on where there's a proton visible. Okay, and so the electrons would be oriented to the protons in the nucleus, and they would be repelling each other, obviously, and they would be repelled by the electrons in the nucleus, and they would acquire a balance in their configuration. So unfortunately, these arrows these arrows don't help. Anyway, so you start with something like that, and then you'd say, where would the next electron be? Obviously in these positions. Where would the next electron be? Obviously in positions where they can get as far away from other electrons, blah 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 blah. So it's all a geometric thing. All right, and the Stern-Gerlach is basically saying, okay, all atoms aren't this symmetrical. Okay, most atoms don't have a perfect symmetry, and they end up having, oh, we got an extra electron out here. All right, so let me put a big X on it. So that's a silver atom. So it's got this one extra electron that screws up its balance. So you could argue that it has, because of these electrons, it has almost an equal number of electrons and protons. When you add up the protons in the nucleus and all of the electrons, you end up with an equal number. So you have a balanced atom, essentially. And this, okay, messes up the balance. So you could argue that this is an incredibly weak magnet, in the sense that it has a tiny bit more north and south. There's a tiny, small distinction. So it's a very, very weak magnet. So like even one of those ones from the old days, those stupid ones when I was a kid anyway, you could barely pick up a paper clip with them. They were so weak. Okay, so an old crappy iron magnet that's been banged around a few times and is lost 90% of its magnetism. That's sort of a fair definition of the polarity of a silver atom. It's not a strong magnet, it's an incredibly weak magnet. All right, and the simple argument is we're going to put this very weak magnet into a magnetic field. Now they do all this contriving, okay, of a magnetic field. Now he's going to assert that if you use regular plane magnets, that is, if you send these silver atoms through just a regular magnetic field, north-south, okay, nothing happens. I'll say I've never seen that experiment, so show me, would be my first statement. And my second statement would be, well, yeah, the problem is that this field isn't going to be very strong. So it's not about distorting the field, that is, making, what they basically do is create a circumstance where the north field, let's say, is bigger, okay, than the south field. Like you're using a big magnet on one side and a weak magnet on the other side. So they're looking for a configuration to do that. So the original Stern-Gerlach configuration was something like this. All right, and the idea is that here is where you're going to send your stuff through. And so you have a concentration of the north side and a weakness of the south. Yeah. And what the more modern version of that is they do something like this. Okay, to create the same kind of disproportion in the field strength. Okay, so and the bottom line though is it doesn't matter what you do, because the idea is that their argument is that you're going to send these weak magnets, so they could go in any orientation. So you can understand it's north-south, and the atom is going to be going through in various conditions. Okay, in terms of where that extra electron is. So we're just talking about where the electron is on the surface of the atom as it travels through the magnetic field. And the simple argument is that no matter how you shape this magnetic field, and if you want to make it stronger north to south, if the atoms themselves can't orient, that is flip, because they're so weak. So you understand, to flip the electron, okay, by a different model than their model, to flip, the electron has to drag the whole atom with it. So all the electrons, all the, the one extra electron out here has to apply a torque, okay, that would be significant enough to move the entire atom, to move all the other electrons plus all the big heavy protons. It has to turn everything. And so it's pretty impractical that it's going to do much turning. But the force, the fact is that it still is a magnet. It has a net difference. And so it's in a field, okay, and let's just say the field is just pushing primarily in one direction. You could sort of argue that the south side is weak, the north side is strong. So it's a big, strong north side field. Well, the fact is it's going to attract anyone that's got the north end opposing, in the wrong direction. Well, that one's going to move this way. And anyone that's got the extra electron, let me put that's the other way. Yeah, no, sorry, that's the wrong. Well, they're going to be inverse in their direction. That's all you need to know. So these would be pushed away because it's the wrong, there's more north facing north. And then there's north facing north here. So those are pushed away. And when it's south facing north, then it's attracted. And so all you're really doing is just saying which way is the silver atom goes in an orientation as a magnet, and which way is it pointing, south or north. If it's pointing this way, it goes this way. If it points this way, it goes that way. And that's all you're really saying. And that they really can't do much turning because they're such a weak magnet. So it's like a really weak, can't even, like say you dope the iron filings with another metal and make the iron filings incredibly poor conductors of magnetism, inducers. You could imagine that the field lines around a magnet are going to look completely different because the filings aren't going to create a very strong magnetic field. Alright, so basically that's the experiment. You're just pushing atoms through, and the simple argument is if they don't turn, because they don't have enough of a polarity to create the turn. There's not enough differential in the north and south strength of these magnets to actually turn them. So, but you can still deflect them. So you can still push north against north, and you can still have south pointing towards south and push them this way attract them. So they still have the capacity to attract and repel, but they don't really turn. So they could also do this experiment by just sticking one magnetic pole in the experiment to see what they do. So instead of this convoluted arrangement, just have a big north side magnet on one side and then push them through and see what happens in that case. And if you still get deflections in both directions, you'll know, oh yeah, this isn't about anything, in terms of some electron spin. It's just about whether or not, the atom is oriented north to a north or south to a north. And so the speed that they're going through here makes the difference. So the faster they go through, obviously you could understand they're going to get deflected less, and the more the slower they're going to be deflected more. And so basically that's all you see in the experiment is you gradually push them, spread them, and then you spread them. And the stronger you make the magnetic field, the more you guarantee that every single one of them will be moved, even if their orientation is going in perfectly straight would mean they don't drift much at all. But the definition of perfectly straight would be what we're really arguing about. So you have two conditions. You could have a very slow atom that's perfectly straight, perfectly parallel, anti-parallel to the field, perpendicular to the field. And so it wouldn't be attracted or repelled. And so, but again, perfectly straight. And so the argument is none of them are perfectly straight. So if I increase the field, the little tiny difference will make a difference. So the slow ones that go perfectly straight, if you increase the magnetic field, they'll finally move. And very fast ones that have a very crooked, they're really polarized, well, the stronger you make the field, the more likely they are to be bent too if I increase the field. So you can understand the diagram, okay, pretty clear. That you don't need any complicated spin theory. All you need to do is accept the fact that they're magnets, okay, and I guess I need to erase that. And that all you're really doing is saying they're so weak that spinning, turning to the magnetic field isn't really an option, because there's not enough of their material that's going to be capable of doing that. And so you start off with them all straight, no magnetic field. You apply a magnetic field, and they start separating based on whether they're this way or they're this way. So if they're this way, they go that way. If they're this way, they go that way. And that's all you're seeing here. It's too simple a pattern to, to extrapolate all the complexity they're throwing in there. And they're throwing in all these conditions when there's zero. I mean, we're provided zero evidence. I mean, I think I can just click on this, and you should be able to see this, right? Yeah, the Wikipedia page. There's nothing here, okay? I mean, there's no image that they saw. They don't even show the original experiment and they took photographs of. It's not even here. And it's all 90% of the page is about this spin crap. That's an extrapolation. So instead of just describing the simplicity of the experiment, which is, well, they're really weak magnets. Okay, it's not silver is not strongly magnetic. The atoms aren't strongly magnetic, so you're saying that it's only one electron out of, say, 50 or 60 electrons, and that's the only thing making your magnetism. It isn't like you have a 20 on one side and 40 on the other side. It's not a strong polarity. It's a very weak polarity. And you'd have to, again, believe that the electron spin is somehow moving the entire atom and with its momentum. And somehow it's stopping spinning and running down. Its spin energy is somehow torquing on the entire atom. It's just... there's no good reason to believe any of that. And so, yeah, so let's just play the video. And, yeah, that should do it. And we'll just go through the pieces and his description. And, again, part of it is a concession, in the sense that he's pointing out how, well, look, there's this myth of the Stern-Gerlach experiment and why it was done and how it was done, and then there's the reality. And my argument is not even fully describing the reality. Because, again, why not the simple experiment first? Just show me what these atoms do when I put them between just two regular magnetic poles. And they have to be very strong, of course. And so, again, we're talking about nothing's going to happen if it's a weak field. So, again, we're just saying, okay, can you create enough of a magnetic field? And that's all this is really talking about. All right, so leave us play the video and such. I'm going to check the volume and whatnot. All right, that should be close enough. So leave us continue.
In 1922, this experiment separated electrons into two groups, conclusively showing quantum spin.
All right, so this is just crap. Okay, I mean, clearly they're gigantic whole atoms that are in the experiment. That's what, Stern-Gerlach didn't measure them with a detector. They just let the silver atoms deposit on a plate. So, the way they detected them was a little different, and so they couldn't just they'd have to restart the whole experiment to increase the field and all that kind of stuff. So the more modern experiment, they can trace right on top of their previous experiment, so you can get a clearer indication of what happens when you increase the field.
Except it wasn't electrons, they didn't form two groups, and quantum spin was not the conclusion the scientists came to.
So it did create two groups, so I don't know why he's disagreeing with that. It clearly creates a clear separation, and so I'm not sure why he's saying that, but whatever. So he's pointing out how the hype isn't the real experiment and isn't real purpose. So quantum spin wasn't a thing when Stern-Gerlach did the experiment, but angular momentum was, since in the sense that they believed that the atom has a bunch of electrons going 450 million meters per second or whatever the fucking speed is, spinning around, and that somehow that makes for strong atomic bonds. is to have a bunch of stuff swirling around at impossible speeds. No, it doesn't. There's just no reason for you to think that electrons are moving, around the nucleus. There's just no reason to think that's a thing. And it certainly isn't conducive to all the chemistry you see. Do they ever show the molecule doing this, spinning? Do they ever do that? No, they show you a molecule with electrons and protons in positions. All right, they don't show you something spinning all over the place. And then they could show you how it connects. And, the whole thing works with a model that's magnetic, not a model that's got a bunch of wooey spin gravity crap in it.
Here's what really happened. Hey, crazies, what we're talking about here.
So this whole crazies thing, it's a shtick. You ought to just get rid of that, frankly. Let's all be childish. Now let's not bother with that.
Is the famous Stern-Gerlach experiment.
Gerlach, I think is better, but okay, whatever.
Conducted by these two guys. To be fair, this experiment was evidence for quantum spin. They just didn't realize it at the time.
I mean, it's just so, how is it evidence in the sense that the one electron is going to somehow move the whole atom? I don't think so. No, it's spin. Yeah, no, not going to happen. All right, continuing. So again, this would be really great if we had a whole bunch of experiments, regular magnets, all kinds of different configurations, showing us these distinctions and showing us how there's no similarity here and nothing, but we don't have any of that. So it's not really good science in the sense that we're giving a tiny amount of contextual information. Again, it's like the two-slit, never photographing the two sides to see if the pattern actually goes at strong angles. No. Don't bother. No. Never even investigate. Nothing. And it's just junk science, and this guy, frankly, he knows enough about this stuff to know that yes, they have talked a lot of crap, and he ought to just admit that this isn't real solid science. This is just all mushy talk.
Stern and Gerlach were trying to prove space quantization of angular momenta.
Which doesn't make any sense, right? I mean, this whole idea that somehow the electrons are spinning around the atom and it's quantized doesn't really make much sense, okay? To say, that it's a quantized spin when you'd have to figure that the ones on the inside are under a higher pressure than the ones on the outside in the first place, and that the whole thing is rotating together. Yeah, well, that's an argument you have to deal with, because the electrons have to be spaced away from each other. So when he shows the drawing of the electron orbitals, I'll point out the obvious defect in the fact that they're not recognizing that electrons hate each other, that they create an opposing force that's real, and that's the force that's creating this idea of even being in space, separated from each other, is the fact that electrons can't get close to electrons, and they just keep ignoring that fact.
Or in plain English, they were interested in measuring magnetism caused by electron.
So you know that those electrons, the ones on the further out, the ones closer in, that they're all applying a repulsive force that they can sense. They sense each other's positions based on a field that hits them of energy. Okay, and so they can't be in positions where they fly right next to each other or something. They can never do that. They can never fly into each other without having a reaction that's going to be equal to the action of getting too close to each other. So they're going to constantly be measuring each other's momentum and maintaining a distance from each other.
Orbits. The idea that the particles themselves could be spinning? Not even remotely on their radar. To understand how they could have missed it, though?
Well, it's remotely in the sense that it only took a couple of years later where they reinterpreted the experiment into something called electron spin. So it wasn't much later.
Oh, we need some historical context. In 1922...
I wish you'd go back to 1690-something, 89 or whatever it is, when Leibniz published a year before Newton, okay, and proposed that 4 pounds dropped 1 foot is the same energy as 1 pound dropped 4 feet. I wish you'd go back to that one and analyze that one and say, oh yeah, they proved that with lots of experiments, when they didn't do a single experiment.
The leading model for atoms was the...
Okay, so this, look, the electrons aren't spaced proportional to each other. So you see this electron is closer to this one, further away from that one. That kind of crap ain't going to happen. They're going to have to be in a symmetry, okay, in terms of their positions, where they can balance their hatred for each other. So you could just say, okay, the electrons have to balance their dislike for each other. And so if one part's spinning, then all of it has to be spinning, and it has to all be connected. But the point is there's no reason to think it spins, because it doesn't help. It doesn't help make molecules. It is exactly anti-molecular. It creates all kinds of problems that mean molecules can't exist, because they would have to be stuck with all of this momentum. If some other atom connected to this atom, all of this momentum, it would have to meld with it. It would have to say, okay, I'll spin around you, or you'll spin around me, but somebody's going to have to spin around the other guy, and that just ain't going to happen.
Bohr model. Electrons orbiting around a dense clump of protons.
So again, it's a clump of protons, and why is it dense? Well, because there's electrons between the protons. I mean, this argument is just so simple, and it's just, it's so depressing, that they never even thought about it. That if I wanted to get two north magnets close to each other, what's the simple solution, right? You just stick a south pole. That's too bad. It's a nice color if it would show up. Yeah. It's always something. Ruined my fun, damn it. All right, let's try this. Okay, it doesn't look very southy, but anyway, so I put a south pole between the two norths, and I'm going to be able to tighten everything up really tight, no problem. So if you just think of electrons and protons as magnetic monopoles, which they are, okay, you just make a magnetic model out of that atom. You just say, okay, I have electrons and protons in the nucleus. I have twice as many protons. That means it's proton, 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 electron, electron. 2 electrons for every 4 protons kind of idea. End up with a helium nucleus, by the way. And that everything else is made out of just multiplying those helium nucleuses. Okay. But anyway. Let's continue. Just so bad.
And probably something neutral we hadn't discovered yet.
Right, something neutral. Neutral why? Oh, because it's a dipole, because it has both poles. So it looks neutral from a distance. From a mile away, it looks purple. Up close, it's blue and red. Not very complicated. I mean, there's no way they have proven that to be an impossibility. There's these alternative models haven't been tested fairly. They haven't been considered fairly. They just sat there and jumped on their bandwagon of, well, the Holy Ghost. Isn't that a great concept? We'll do the Holy Ghost. And that's all spin is. That's all entanglement is. These are just Holy Ghost fixes. Hobgoblins and gremlins.
Anything going around in circles, like those electrons, has something called angular momentum. You can think of momentum as a kind of interaction currency.
Right, and it's going to be a huge problem in terms of balancing it in interactions with other atoms, and it just ain't going to happen. One atom's going to be spinning more than the other atom. How they're going to combine? I mean, it's just, forget it. No possibility that you could keep an atom. You wouldn't break the thing into a million pieces. Trying to combine anything with this silly, wooey velocity model of atoms.
It can get exchanged between objects when they interact. Angular momentum is just momentum associated.
Yeah, it's nice that you point that out. Why don't you just say it means nothing? The word angular really doesn't mean anything. It's just particles, masses moving a velocity. It's just momentum. And it just happens that the momentum has some mechanism that's forcing it, okay, to be in a circle or in some other shape of you know, non-linear. But it's doing exactly what linear momentum does in terms of that's its only strength, is the fact that it's a particle of mass moving a velocity. It's just momentum. There is no angular kinetic energy.
Associated with arcs, orbits, and spinning. You know, anything you might assign an angle to, hence angular. For things like planets and stars, there are always smaller denominations of this momentum currency. It's like digital money, where you can exchange fractions of pennies.
So this part is just the argument about, is there an elemental bit of force? Is there an elemental bit of mass? And my argument is, yeah. Electron, proton, elemental mass, and the force bit, the force quanta, the light quanta, is, yes, there's just little tiny bits, and you can send a bit of frequency and they'll look like a photon, or you can send them in a pattern and it'll look like magnetism, and you can do lots of things with these little bits. But yes, there's just little bits to exchange. Those are the pennies. There's nothing smaller than the penny. That's the argument. You can never give somebody a half a penny.
But for electrons, this angular momentum is quantized, meaning it can only take on certain values. In other words, the denominations are fixed. You know, like paper money and coins.
And the only thing fixed about the atom is that the further away the electron is from the nucleus, obviously, the less secure its connection to that nucleus it's going to be, because the proton that's attracting that electron is very, very far away, and there's a very reduced amount of energy holding it there. So the electrons on the outside are easily kicked out. The ones on the inside, really rubbery, really strong bond, because they're very close to an electron. Yes, they're also very close to, a proton. Yes, they're very close to other electrons, so they're under a bit of high pressure, high tension. But they're not easily jarred out of that tension. So the ones on the outside, easy to knock off. Ones on the inside, hard to knock off.
Only certain orbits are allowed inside an atom, and nothing in between. This quantized...
So this weird, bizarre idea that somehow there's some mechanism in the universe that regulates exactly how fast the electron goes, and it can't go any faster. We know orbits only work, even orbits around magnets. They are very specific. A little bit too fast, you fly out. A little too slow, you fly in. We know it's how complicated orbits are. So again, it's a silly model. It's silly. There's no possible way all this is being regulated by some magical mechanism that's regulating exactly how fast the electron moves. Come on. It's ridiculous.
This model explained quite a bit about atoms, and so it wasn't really up for debate.
Oh, so there's the magic words. It's really not up to debate. One guy will tell everybody else what to think. And because all of you have no imagination and never even drew a picture of it, again, this picture, right? It's still on the screen, right? This picture's still on the screen, isn't it? Yeah, right there. You never even thought that if I want to get two protons close together, that the obvious answer is just stick an electron between them? And bingo, solve the problem. I don't need a strong force. And it's impossible that that's the answer. Impossible. You've proven it with some kind of experiment that proves this couldn't be the simple answer. Yes, electrons are attracted to protons. Protons are attracted to electrons. Gee, it seems like a perfect solution. Oh, God. But it's not, we're not going to debate it. We're not going to entertain it, because you're all just flat earth religious kooks sit there. You got this wooey theory that you've all invested in, and you're just obnoxious to being told, well, guess what? You chose badly. Again, 300 years ago, Leibniz says 4 pounds dropped 1 foot, same as 1 pound dropped 4 feet. You've never tested it. It's only 350 years later. We landed on the moon, and we landed on the moon using momentum, by the way. Do you really think the lunar module used kinetic energy theory to land on the moon? I think you know. Nick. They calculated the mass and the velocity of the thrusters, and that's how they decided how much energy it was going to give the lunar module. Because guess what? The Newton's third law only works for momentum. It doesn't work for kinetic energy. Oh, I just can't believe I have to do this for years. And these people are just so unfair. They won't engage in this argument. I mean, they've catastrophically broken physics with fables, and they won't have their fables torn down by simple logic.
What was up for debate was the orientation of these electron orbits. Could electrons orbit in any orientation they wanted? Or were the orientations also quantized?
So all this woo, and just like I said, if you take that center thing and make it blue and red, indicating protons and electrons, twice as many red things as blue things, and then you just say, where can I stick another blue thing where it sees the proton really well, but there's other electrons on the outside that are going to repel it. So it really can't go in because then it gets too close to the electrons. Okay, and so it gets stuck in a position, a magnetic position of equilibrium. What's wrong with that idea? How does it catastrophically fail? Oh, it doesn't, and they won't even listen to it. All right, a bit of a life distraction and such, so I don't know where I was, but we'll just continue.
Stern-Gerlach devised an experiment to test just that. It all starts by...
So again, the test is somehow that this tiny difference in the polarity of the atom will somehow, and this little one electron, its angular rotation around the atom will somehow turn the whole atom, and, not likely.
Placing a piece of silver foil in a really hot oven. It's so hot that silver atoms sublimate off the surface and bounce around inside the oven. At least until
vaporize, yes.
Some of them escape through a tiny circular hole in the side. After that, a slit filters those atoms into a beam. That beam of atoms is what they were running their tests on, and they chose silver for 3 reasons. It was easy to acquire, it was easy to vaporize, and most importantly, the outer shell of the atom only had 1 electron.
So you're just looking for a polar atom, an atom that has an asymmetry, because the outer ring, it doesn't have, isn't full of electrons. So there's always more on one side than the other side of the atom, in a sense. And so it's a very weak magnet is the real point. So out of the, whatever that, I'll guess that's 30 electrons. And then you figure there's another 30 inside the nucleus, and then there's 60 protons and something like that. And you're talking about 1 to 60. It's not a very strong magnet. Simple enough argument.
Bohr model says 46 of the 47 electrons in silver would find some kind of balanced configuration, where their angular momenta cancels out.
So again, this idea that the momenta cancels out or that the momentum stops. So their whole point would have to be that somehow the atom stops spinning, because if it's spinning, then you're not going to be able to see that it's polar, right? Because the pole just keeps going. Oh, Jesus. It just keeps, the polarity keeps moving past you, so you can't really, it's like you can't, if you spun a magnet, you can understand that if I spin a magnet really fast and then put it through a magnetic field, it's not going to do anything. Oh, shit. One of those days.
The single electron in the loose outer shell would hold the only remaining angular momentum in the entire atom.
So that doesn't even make any sense. It's the only angular momentum. All of them seem to be spinning, so what are you talking about? It's the only angular momentum, and it's tied to, if you understand that it's tied to all the other electrons, it's a huge amount of angular momentum.
In other words, while the atoms had many electrons in them, they only had to worry about 1.
So again, it's the 1 is as like a flipper or something. So if it's tied to all the other electrons, then you can say, okay, the angular momentum is pretty strong, and you can use this 1 magnet to move all of them. But it's still a ton of energy or momentum that you have to convert to move the whole atom. So regardless, And what are we really talking about? Are we talking about spinning left or spinning right? Spinning forward, spinning backward. It's way too complicated a mechanism.
Ugh, genius.
Oh, Jesus. No, fable, religion, another religion, the religion of the magical electron. They have all kinds of, magnetrons. They have all kinds of, magical words for their mechanisms.
This beam of silver atoms was immediately sent between two magnets, one forming a channel and
So I don't know why he says immediately sent. There's actually a distance, so it's not that immediate.
the other a knife edge. These shapes were important because one magnetic pole needed to be stronger than the other.
Why? And where did they prove that? And where's the experiment showing a more symmetrical magnetic field? We don't have any of those experiments.
If they were the same, nothing would happen.
Says you. See? So he says nothing would happen, but we don't have. Where's the experimental proof that nothing would happen? Oh, that's right. We don't have that.
The orbit of that outer electron creates a magnetic field that should respond.
The point is that this concentrating the field, making this distortion, it creates the ability to move magnets that aren't going to flip. So the whole point is, if you can't flip the magnets, this is the kind of field you want to create, because it still pushes and pulls, but they don't flip.
Onto those two magnets by deflecting in one direction or the other, ultimately depositing on a glass plate. The debate was over what direction the atoms would deflect and by how much. We've got two possibilities. If electrons can orbit in any way they wish, then each atom in the beam will have a random orientation.
So again, it doesn't mean anything. Random orientation in what? If they're spinning, then they don't have any orientation. So again, if you spin a magnet, it's just a literal truth. You spin it fast enough, it's not a polar magnet anymore, because it all turns to purple. Again, you're trying to make it red and blue like a magnet. You have red end and a blue end. I spin it fast, you're going to see it's purple. Okay, you've lost its polarity. So the very idea of spin breaks polarity.
The atoms more aligned with the magnets will deflect more, and the atoms less aligned will deflect less. The pattern on the glass plate should be a spread of silver atoms.
So, and that's initially you get some of that, and then the stronger you make the magnetic field is where you start to just cut everything out of this center and move everything this way and that way. So he's using up and down, where, the experiment's left to right in other cases.
However, if the orientations are quantized, then only certain orbital planes are allowed. The atoms in the beam.
So whatever orbital planes could mean, it's a pancake atom or something. Who knows what he means by that? And clearly this has nothing to do with this diffraction pattern kind of crap. It's not really a diffraction, it's an interference pattern, frankly. So I don't even know why this is part of anything, because nothing like this was shown in the experiment. So I don't even know why this is an illustration.
Beam should only deflect specific amounts, forming distinct groups on the glass plate.
Silly explanation, frankly. The atoms are all going in with a different orientation. There'd be no way that you could take one atom and put it over here, and then another atom's configuration, it goes to this exact spot, and this. No, none of that would happen. You're just having a push-pull. You're just pushing or pulling depending on which way the South Pole is versus the North Pole. And that's it. If the extra electron is on this side, it's going to go that way. If it's on this side, it's going to go that way.
The pattern should look more like these. There was just one problem. They didn't get either of those patterns. This was their result.
All right, so this is pretty ugly, frankly. So I don't even know what to make out of it. So anyway, it's basically saying some extra were pushed this way for some reason. I don't know what this peak little thing over here is. So this, I guess, has to do with the orientation of the beam. So they have the beam going through with the field this way. So they're pulling the beam up and pulling the beam down. But regardless, it doesn't really matter. They obviously they're not taking a beam this way and pulling it that way and pulling it that way, apparently. So I don't know. Obviously, this image isn't on the Wikipedia page. Well, no image is. But what this is exactly an image of, who knows? Again, this little peak thing here is really distracting in terms of what the hell does that represent?
Which is much closer to our second option, but not quite the same. Thankfully, Stern-Gerlach thought to do the experiment without the magnets.
So clearly, when they did the redo of the experiment in the 1950s, you get a much teardrop kind of pattern. So it's a much more understandable pattern.
And the result looked like this.
So that is pretty much just a spreading pattern, but again, no dip in the center. So somehow no lessening of the number that go dead straight. So you're pulling them in these directions. No, this is just a straight line. So this is just saying nothing happened, right? Because they're doing the experiment with the beam going this way. I don't know. The beam is a slit beam. It has a length to it. So I don't know why these images are so incoherent to understanding what exactly you're looking for. Is the beam going this way or is the beam going this way? So is that what this is? This is just the beam.
The horizontal spread was still there, which means it's a problem with the slit filter and not the magnets. It's an experimental error, but it's one we can correct. Let's take the...
So I don't even know what he's talking about here, but okay, so they made an experimental error of some kind? I don't know. What's the point of this crap?
Deflection result and remove the horizontal spread. And would you look at that? Orbital orientations are quantized.
Oh, I mean, come on. So what was that? So he's just taking the results and saying, let me modify them entirely. That's a complete modification of the results, that they all went to a specific location at an exact intensity, and that didn't happen. They either spread or they group, but there's none of this, one specific location, they all go to that specific location. That didn't happen.
The experiment was a success. Or was it? In 1922, when this experiment was done, it seemed like a perfectly reasonable conclusion.
I showed the other pattern, right? So, it's kind of obvious that pattern just said, okay, you're taking a straight line, you're putting them through, and they start to drift in the two directions, and then they get to a point where it's all over here and all over there in equal amounts.
One, frankly. But then 4 years later, some guy named Erwin Schrödinger came along and broke everything, and promptly rebuilt it with the help of his friends. More specifically, he published this equation, and its solutions were revolutionary.
They don't have solutions, frankly. That little forky thing means all the information about the system, and they don't have all the information about the system, so it's just bullshit.
We learned there were different types of orbitals that electrons could occupy. Each of those orbitals allowed for only certain values and orientations of angular momentum.
So again, they keep talking about angular momentum having some kind of effect in some sort of real way, and all the angular momentum would do is get in the way. You can't combine things that are spinning. There's no way you're joining atoms that have angular momentum.
So far, that might seem like it aligned quite well with the Stern-Gerlach experiment. But like with many things, the devil is in the details. The outer
and there are no details, so that's the problem. And so there's no point in saying the devil's in the details. The devil is in the absence of detail, the absence of any context, the absence of various experiments changing the magnetic field and seeing what happens to the result. All of that valuable information is missing from this analysis.
Electron in silver is in what we'd call the 5s orbital. But Schrödinger didn't just say that s orbitals exist. He said they have a set of properties that make them s orbitals.
So there's no properties. They're all electrons, and all the electrons have exactly the same properties, and all you're really saying is the condition it's in, how far it is from the nucleus, means that it's bound weakly.
One of which being zero angular momentum. Yes, you heard that correctly. This outer electron
it has very little energy, obviously, in the sense that it can't do much hitting or kicking or all that stuff, because it's such a little, it has such little tension with the atom. It's not connected hard, so it's like a very weak paddle. It's like hitting it with it's like hitting something with feathers, because it's so weakly bound. It moves readily, where the other electrons, depending on how close they are to the nucleus, are harder and harder and stiffer. But that outside electron, very weak.
Doesn't have angular momentum, like at all. How can they get away with that nonsense? Welcome to
whatever the part of whatever they get away with, whatever part is the nonsense. So it's nonsense against nonsense, in my opinion. Religion against religion. This is not the truth. This isn't reality. So they're talking some crap they've made up. Okay, it doesn't really work, but they claim it does. They can't really draw you any picture of it, right? They can't really draw you this picture of this. They're showing the atom moving really slow and the electron. No, I mean, this thing's moving insane speeds. Okay, and then the two atoms are supposed to collide with each other and somehow share an electron. How the hell are they going to do that?
Quantum mechanics. And I don't mean nonsense like it's not a real thing. This is very real. I just hate it.
No, it's nonsense, and you should hate it because it's not a good answer, and it's giving way too many properties to the simplest things in the universe. The elements of charge are so dependable and so reliable and so consistent. It's just idiotic, all right, to say they have all these flavors and all of these different functions and features.
Anyway, this is when physics started to reevaluate the Stern-Gerlach experiment. For 4 years now, they thought this experiment was showing orbital orientation, but that couldn't possibly be true anymore.
So again, and there's no reason to not recognize that all that it's showing is that you can push on the north side of a magnet, and then you can turn the magnet around and it'll pull in the same field. So the field, just turn the magnet and it'll go one way, turn the magnet the other way, it goes that way. And that's all this experiment shows, okay? So there's nothing else it's showing except merely magnetic deflection. And you're using just one pole of the magnet to do the deflecting. So you're just basically saying, as long as the magnet can't turn, I can push it or I can pull it. Simple explanation.
If this electron has zero angular momentum, then so does the entire atom. No angular momentum means no magnetic effect.
So he's saying that the magnetic effect is being created by the angular momentum when it's completely hostile to the magnetic effect. There's no magnetic effect if you spin the magnet. Again, if you take a magnet and spin it north-south really fast, you're just basically saying that what's it going to do in terms of move? Well, it's obviously half the time north and half the time south, so it's not going to move at all in a magnetic field. It can't move in the field because it's constantly flipping its orientation. So it's, the idea of momentum spin defeats magnetic polarity. It takes the polarity out. It's like a compass needle, so do that, right? You spin the compass needle, and it's not till the compass needle slows down that it can start to orient to the field. But it can't orient to it at all while it's spinning.
Which means no deflection. The Stern-Gerlach result should have looked like this, a single dot in the middle of the glass plate.
Now, why would you think? You're putting polarized atoms, magnetic atoms, single atoms that do have a magnetic property, very weak, but they have it. You're putting it through a magnetic field. Why would you expect it to be a zero result? You know that the magnet will move in that field, so why are you expecting it not to move?
This posed a problem because that's not what happened in the experiment. We know these atoms are deflected in a quantized way.
No, what you really know is they're deflected in an equal way. That is, half of them go one way and half of them go the other way. Completely symmetrical, indicating that that's how they go into the experiment. They go into the experiment with one orientation or the other orientation, and there isn't any other orientation. They're either lefties or they're righties. And they just show you whether they're a lefty or a righty. And how left and right they are is deciding how far they're pushed in the magnetic field. Also, how fast they're going.
And we know that it's due to magnetism. Your first thought might be that these particles have some kind of inherent magnetism.
Oh, yeah, yes, electrons and protons are inherently charged, which is the same damn thing as being magnetized, okay? North-south behaves just like, I mean, if you really could just break magnets and get a north magnet and a south magnet, you'd see that they're going to behave essentially just like charges. There's not going to be any difference in their behavior. The north-south will be attracted, the south will repel, the north will repel. They'll do exactly the same thing as charges, electrons and protons. So again, fail.
But that doesn't check out either.
Says him.
If they were just tiny magnets,
Yes, that's all they are. And look, in the 1950 version of the experiment, they go to some lengths to point out that they're tiny magnets. That's exactly what they are. They're tiny magnets. You're going to throw them through a magnetic field at varying speeds. And the surprising fact is that in this uneven field, they don't turn.
they'd reorient to align with the field and they'd all deflect the same direction.
Right. So again, he's arguing they would reorient even though, wait a minute, they're not really magnets like strong magnets. They're incredibly weakly magnetized, only a tiny bit of polarity. And so only as a whole can they be seen as generally red and blue. So when they're in the field, that will be realized in the sense they will be net pushed or net pulled. But it's a tiny amount of, it's only the one electron that's making the difference.
That's also not what happens.
Says him. So no evidence that's not what happens. So he just says it's not what happens. Yeah, he's not going to prove that's not what's exactly happening. Except for the turning part, obviously. If there's, the stronger the magnet, the quicker it turns. Everybody can notice that. You play with magnets, you'll see. Weak magnets, slow turn, strong instantly turn.
We need something that causes magnetism and doesn't allow for reorientation.
So we already have that weak magnet. So anyway, again, back to this angular momentum nonsense. All right.
Brings us back to good old angular momentum. But if it's not orbital angular momentum, then what is it?
So now they're going to invent the moon spinning. So it's not the solar system moving, okay? No, it's just the spin of the moon is going to control the entire solar system. Not likely.
Thankfully, in 1925, Uhlenbeck and Gaudsmit had already suggested the answer: quantum spin. That came 3 years after the experiment, but 1 year before Schrödinger's upheaval.
All right, so in my opinion, like I said, there's no reason to not recognize all the torque mechanisms that exist in an atom when you make it magnetic. It has a ton of mechanisms tying the whole thing together, and meaning that when you move one object, you have to move the whole object. So there's all kinds of reasons to think it really matters when you apply a torque to an electron. Okay. But it has nothing to do with spin. And it certainly doesn't have anything to do with you're saying this is a part of the energy in the atom, is the motion of the electrons around the nucleus. Maybe the whole nucleus is spinning too, so it's even more momentum. And then you put this one little stick on the outside, and somehow the one little stick is going to whack things all over the place. And not going to happen. Because the one little stick is so weakly held to the atom. It can't apply a torque to the whole atom.
So they couldn't have suggested spin in response to this experiment. As far as these guys were concerned, the experiment was just fine. They were suggesting it for an entirely different reason. It just coincidentally also solved the Stern-Gerlach problem.
And there's no problem, right? The Stern-Gerlach experiment what's the problem? You put a magnet through a magnetic field and you saw them do exactly what you would expect them to do, which is move differently. Yeah. So what's the hang up?
Once we realized there was one. But here's the craziest part of the story. If Stern and Gerlach's intention had been to measure quantum spin, they would not have thought to run an experiment like this. They would have wanted to take measurements of free electrons.
Okay, so this whole thing of these are actually free electrons is, again, another doubtable statement. And these are only visible electrons because you either put a gas in the tube or they're hitting a plate, a fluorescent plate. So you know, these experiments have details and variables in them that, frankly, they don't really account for. You can see the cathode and the anode are very differently colored, meaning that there's all kinds of atomic atoms being moved. You're basically plating one. You're taking the cathode and spitting it at the anode. Okay, and basically plating it with atoms. So let's not pretend that, oh, we're quite sure this is just a perfect stream of electrons. Now, of course, electrons will be bent in a magnetic field. So it just makes sense that, yes, of course, they're going to be bent because they're the magnetic monopoles. But it really depends on the orientation of the magnetic field because, frankly, the electron has the same problem. Let's say I had a magnetic field facing an electron coming directly at me. If the magnetic field is a pattern, that is a bullseye pattern, you have a proton, you have two electrons, they create a pattern, okay? You can understand that from one distance, the pattern's going to look a certain way, and as you move closer, you change where those things meet, where those vectors meet, in phase and out of phase, and all of a sudden, then it's going to be repulsion, and then it's going to be attraction, then it's going to be repulsion, and so the electron's going to have a hard time moving. But if I do it at an angle, then I can push an electron sideways because there's no interpretation of the field. That is, it's just obviously going to be either conducive to pushing because there's going to be more red visible than blue visible. So it gets a little complicated, but frankly, it makes perfect sense that electrons are bent by a magnetic field because they're magnetic monopoles.
Like the ones in this beam. But beams of charged particles are already deflected by magnetism, just by being moving charges.
Yes. They're deflected because they're charged.
No quantum mechanics necessary. That would have hidden any deflection they might have been able to see from quantum spin. So their initial hypothesis being wrong gave us a vitally important experiment. It was a happy accident. We like to think of history as a...
So again, it's a happy accident. Again, and all of this interpretation. So they're taking gigantic silver atoms, throwing them through this crude mechanism, and then claiming they're detecting the spin of one electron. Now, does that sound realistic to you? So a 1/60th or 1/100th of the mass of the atom, okay, it has a little bit of a spin, and that's going to decide what the whole atom does. I mean, to me, frankly, it's just ridiculous. I mean, it really needs a lot more hashing out and a lot more evidence before you make these declarative statements that, oh, we have the preponderance of the evidence indicates, or we've proven, and that's the kind of rhetoric they use. They have somehow proven this to be the mechanism, and they're so short of anywhere near enough evidence for anybody to draw a conclusion. And they won't really have the discussion about any other theories because they're just closed-minded religious kooks.
Nice, simple narrative, but only fiction works that way. Reality is a messy jumble of mistakes and time.
And yeah, and know what reality does though? It creates lots of straight lines, so you don't have to keep any of these crooked ones anymore. So even this is a poor diagram of logic and how we refine our statements about reality. We get more and more specific, and we get more and more accurate, more and more precise in exactly what we claim to be a mechanism. Punctuated equilibrium being a huge example in terms of evolutionary theory, recognizing that, okay, there's no the missing link fossils. The simple explanation is yes, the evolution happens in small groups, not in big groups. It's really hard for one deviant to spread its genes into a giant pool. So if there's one white buffalo and he lives with 1,000,000 other buffaloes, the odds are he's going to get diluted out of existence. Not that he's going to dominate and control, and win. But he can win if it's just him against one other male somewhere. Then he has a fighting chance to take over, and everybody comes out white. And then you have a big battle someday when the white buffaloes are thriving and doing very well. Someday they just take over. They wipe out the other ones. That's a more precise, a clearer explanation of the mechanism, explains all the missing details, and creates nice straight linear lines. And so this diagram is kind of just horseshit.
Tiny successes that often happen out of order. The simple narrative is only a fraction of the whole picture.
Right, and the whole picture should be the whole picture, which is in 350 years they have done no kinetic energy experiments. Nothing. They're still doing ballistic pendulum experiments where they clearly collect less than all the momentum, let alone collect any of the kinetic energy. So they lose 99.94% of the kinetic energy is missing, and they don't have a problem with that. And they'll just continue to say it's real energy, even though we can't collect it. We're trying our hardest to collect it in the pendulum, and they can't collect it. And they can't even collect all the momentum in the pendulum. And yet they're going to claim it's a real thing, this kinetic energy. I mean, amazing nonsense. Amazing bad science.
And until next time, remember, it's okay to be a little crazy.
No, it isn't. It really isn't okay to be any. It's like saying it's okay to be a little drunk. It's okay to be a little stupid. It's okay to be a little bit arrogant. It's okay to be... No, it's not okay. Don't do any of that shit if you don't have to. Okay? Only be an asshole when it's absolutely necessary. And in every other circumstance, try to be fair, honest, and have integrity in what you do. And don't be claiming you prove something when you haven't even come close to the burden of proof. It's like people calling themselves innocent because they weren't proven guilty. It's just factually wrong. Okay. So, I guess the rest was some dopey commercial. Buy my merch and all that kind of crap, so we won't bother with that. All right. Well, not too bad. 1 hour. Could have been worse. So anyway, till the next time, I'll maybe pick through and see if he's got any other videos. I mean, he's always kind of arrogant, points out that there's a flaw in what somebody else thinks, but he doesn't really prove his case. And again, it's just, he's all in on this woo physics, and it's all just woo. Gravity's a real force. The Earth isn't expanding. I mean, all this silly crap he'll defend as somehow a reasonable interpretation of the data, and it's not reasonable, and it's not fair, and it's not complete, and it's not accurate. All right. Till the next time, and such and so forth and whatnot. Try not to be an asshole. Even a little bit of a one. At least try. At least try.